Okay, so in this question, we're going to have a look at question number 6. And the first thing to be aware of is that our sample has a mass of 500 grams, and it's asking us to calculate the number of nuclei present. Now, we know that the mass of a carbon-14 atom is 14.00 U, and we know that 1 U is equal to 1.66 times 10 to the minus 27 kilograms. Therefore, carbon-14 atom mass is equal to 14 times 1.66 times 10 to the minus 27, and that's going to give us 2.32 times 10 to the minus 26 kilograms. Okay, I should have put the 0.00 there, but not to worry. So that's the mass of one carbon-14 atom. We know that the total mass of our sample is 500 grams. So therefore, the number of nuclei present is just going to be equal to our total mass, which is 0.5 kilograms, divided by the mass of an individual atom. Okay, and that's going to give us an answer of, let's put that into the calculator, 2.16 times 10 to the 25. Okay, hang on a minute, let's do that again. Now, if you use the full value of this answer from your previous calculation rather than the rounded value, you'll get 2.15 times 10 to the 25 nuclei. If you use the rounded value, as I'm going to here, on your calculator, you'll find that it'll round up to 2.16 times 10 to the 25. It doesn't matter either way which one you do, as long as you show you're working. Okay, so that is part A done. Okay, now it then asks us to work out the decay constant. Now, in order to do that, we're just going to use the equation that we've used before, ln2 over t half, and we know that the half-life here is 5,700 years. Now, because I know from looking at what I'm going to do later, I need the decay constant in per second, because I'm going to calculate things later on in seconds. I'm going to convert this into this half-life into seconds by multiplying by 365 times 24 times 60 times 60, because there are 365 days in a year, 24 hours in each day, 60 minutes in each hour, and 60 seconds in each minute. Okay, so if I do that, I will get an answer then for my decay constant of 3 points. Well, let's do this on the calculator. Okay, so ln2 divided by 5,700 times 365 times 24 times 60 times 60. That's going to give us 3.86 times 10. Oops, that should be 10 to the minus 12 per second. Okay, so that's part B. Let me write that out again just to make it nice and clear. 3.86 times 10 to the minus 12 per second. Okay, that's part B. Now part C, we're asked to work out the activity. So the easiest way to do that is use A to the lambda n. Now we know that lambda is 3.86 times 10 to the minus 12 because we've just calculated that. We know what n is because we calculated that up here, the original number of nuclei. So 25. Now, by the way, I suppose you could put that on there because it's the original activity. And that's going to give us a value of 8.29 times 10 to the 13 when you put that into the calculator. And we can then put that in becquerels. Now, if this was in per year rather than per second, this unit would not be in becquerels, okay? So be careful with your units. D, the activity after 2,500 years. So we're just going to use this equation here. A equals A naught E to the minus lambda T. We know what A naught is because we've just worked that out, the original activity. And we know that E is that. And we know the decay constant is 3.86 times 10 to the minus 12. And we're going to multiply that by the time. And the time here is 2,500, but we're going to convert this into seconds. So okay, so maybe all that in brackets. Okay, and that's going to give us our answer, 6.12 times 10 to the 13 becquerels. Okay, so that's that one. Next one is part E. Okay, let's do part E now of this question. So we're going to use the equation n equals n naught e to the minus lambda t. So we're going to work out the number of remaining nuclei. Now we know that the original number was 2.15 times 10 to the 25. We're going to multiply that by E. This is the original number of nuclei that we worked out in part A. Then we're going to do E to the power of the decay constant, which we've worked out previously, which was 3.86 times 10 to the minus 12. Now, because that's in seconds, I'm going to multiply that by the time in seconds. It's in years, so I just have to multiply it by 365, 24, 60 and 60, okay? And that's going to give me my answer, so let's put that into the calculator. 2.15 times 10 to the 25 multiplied by e to the power of, let's put it in brackets, the decay constant multiplied by 11460 times 365 times 24 times 60 times 60. And when we work that out, we get 5.33 times 10 to the 24. And that is just a number, there's no unit because it's the number of carbon, or the number of carbon nuclei. We now need to work out the mass, and the way that we're going to do that is we are going to first of all work out the mass of a carbon-14 atom, and to do that we know that the mass of the mass of a carbon-14 atom is 14U, and we know that a U is 1.66 times 10 to the minus 27 kilograms. So we did work this out before. It gives you 2.32 times 10 to the minus 26 kilograms. So that's the mass of one carbon atom. So what we're going to do now is multiply these two numbers together to give us the mass of carbon 14 remaining, and it's just going to be 2.32 times 10 to the minus 26 multiplied by 5.33 times 10 to the 24, and that's going to give us, let's do that here, 2.32, that's right, isn't it? Yeah, times 10 to the minus 26 times by 5.33 times 10 to the 24. That's going to give us 0.124 kilograms, which is equal to 124 grams. Okay, so that's part E done. Now part F. So part F now requires us to work out the time taken for the activity to decrease to 20% of its original value, not by 20%. So you need to be really aware of that. It's decreased by 80%. to 20% of its original value. So if you think of the original activity as 1, the remaining activity after this time is 0.2. Okay, it's decreased by 80%. So therefore the ratio of the activity now to the original activity is equal to 0.2 over 1, which is 0.2. So using this equation, A equals A naught e to the minus lambda t, we can now work out this time because we know A and A naught, or we know the ratio of those two, and we know the decay constant. So all we're going to do is a over a naught equals e to the minus lambda t. Now if we natural log both sides, we know that when we natural log this, it's going to give us minus lambda t. So therefore, when we put the numbers in, ln 0.2, because a over a naught is 0.2, is equal to the decay constant. Now the decay constant we worked out earlier was this, 3.86 times 10 to the minus 12. That's our decay constant, and it's in the right unit. It's in seconds to the minus 1. Be careful there. Make sure it's not in years to the minus 1. Or that'll give you your answer in years. I suppose that doesn't matter in a way. And then you're going to multiply that by the time. So the time is going to be equal to this divided by this. Now ln 0.2 gives us minus 1.60. That should have a minus on it, shouldn't it? So that's going to be ln 0.2 divided by minus 3.86 times 10 to the minus 12. Okay, and if we do that, ln 0.2 over 3.86 times 10 to the minus 12, that should have been a minus on there, shouldn't it? Whoops. That's going to give us 4.17 times 10 to the 11 seconds, and you can convert that into years if you so desire.